But now you have learned how to control a motor through code and through an external controlling device like a potentiometer. The sketch would look much the same if you used a simple joystick instead. You can see how from a humble beginning you can start branching out and experimenting with different types of hardware, gradually reaching more interesting and capable configurations. We'll do one last experiment for this lecture. We will connect an ultrasonic distance sensor in the place of the potentiometer and use that to control the rotational speed of the motors. The idea is this. The distance sensor will tell the Arduino how close it is to an obstacle. If it gets too close, it will start slowing down the motors, effectively slowing down a prototype vehicle. Otherwise, it will forge ahead full speed. Have a look at lecture 11 if you need a reminder on how to connect the ultrasonic distance sensor. This sensor uses 4 wires, 2 for power, 5 volts and ground, 1 for the trigger pin, and 1 for the echo pin. What we'll do in this third experiment is to show you how to control the speed of these motors depending on the distance between this ultrasonic distance sensor and an object in front of it. So I'm going to make this little vehicle to slow down as it approaches towards an obstacle and speed up to its maximum speed once it goes once there's a safe distance between the sensor and a wall or another object in front of it. So again, we've seen how to use this ultrasonic sensor in a previous lecture, so go ahead and plug it in really quickly. So start with power and ground and the 5 volts into the Arduino 5 volt pin. Then trigger pin is pin 13, digital pin 13. So that goes here. And the echo pin from the sensor goes to digital pin 12. On the Arduino. So plug that into my computer and now running at maximum speed. So I'm putting my hand closer to the sensor, it slows down. So I'm removing my hand from the sensor, it speeds up. Now there's nothing from the sensor, so the motors are working maximum speed. So if I put my hand really close to the sensor, essentially you've stopped. Now what happens if I actually obstruct the sensor is that the motors start up again even though distance is practically 0. So I'd like you to think about this and figure out why this is happening, and perhaps ways of making sure that the vehicle doesn't move when something like this happens. Okay, I'll stop that and show you what's happening with the script. So in our script, mostly the same as in the demos earlier, the addition here is the definition of the pins for the motion for the distance sensor, and of course I'm setting those pins as input and output for the trigger and the echo respectively. And inside the loop I continuously take distance measurements, just like we saw in the earlier lecture on the distance sensor. Then once I get the distance reading, I call the move motors function, pass the distance to it, and then start with a little test. If the distance is above 50 centimeters, then basically move full throttle ahead in one particular direction. However, if the distance is less than 50 centimeters, the speed should vary. So I'm doing a mapping. I map the 0 to 50 centimeters to a value 0 to 255, which represents the speed. So if distance is 0, for example, of course a mapped value is going to be 0 and speed of the vehicle will be 0. Otherwise it's going to be one of these other values between 0 to 255. And I'm outputting the actual speed here. I've got the 255 minus mapped value because what I want to do is if the distance is 0, then I also want the analog write value, PWM value, to be 0, therefore the motors to be stopped. So I'll provide power again because I want to show you what happens with the monitor. So bring up the monitor. See as I'm changing the distance between the sensor and my hand, the values outputted also change. So you can see that at 2 centimeters, the mapped value that is being passed to the motors is say 5, 10, a bit around 10. As I'm increasing the distance, the values increases until I completely remove the obstacle in front of the sensor, and we've got maximum speed at 255. And that's how you can control the speed of your motor using a sensor like the ultrasonic distance sensor. You can imagine the uses for something like this when you're building robots or vehicles. They'll be able to detect the environment and then take appropriate action depending on what is it that they're detecting in front of them. Of course, there are limitations like the one that I showed you earlier. I'd like you to think about why this is happening. So why is it that when I put my finger right over the sensors and block it, you basically have, you don't have the ability of the sensor anymore to provide a reliable reading. Speed is maximum. Is there something we can do to counter this problem? Now that you have seen the circuit in Demo 3, try to imagine how it will behave in a real situation. Can you foresee any limitations? Can you imagine any improvements? For example, in the current version of the sketch, the vehicle would come to a complete stop only when the distance to a wall was 0 centimeters. Is this sufficient? Perhaps it should come to a complete stop a bit earlier, maybe at 5 centimeters. Or perhaps, to be even more cautious, the vehicle should back up slightly away from the obstacle in order to provide room for a turning maneuver. Can you make changes to the Demo 3 sketch and implement these scenarios or whatever other improvements you can think of? Let's have a look at some theory behind the electrical motor. The most common type of a motor is a DC motor. These are low-cost devices that work by connecting 2 wires to positive and negative voltage. Once you connect them to power, the shaft will start spinning towards a direction. This direction depends on the polarity of the connection. To reverse the direction of the spin, just switch the electrical connections. An electrical motor works by taking advantage of the forces generated by a magnet, permanent or temporary electromagnet, and the electric field generated by electrical current as it travels through a coil. The DC motor can spin very quickly, which often is not what we want in our applications. For example, if you are building a mechanism that opens the shutters of a window, you would like the shutter to open slowly to avoid damaging it. A DC motor on its own will try to go full speed immediately. So in most cases, people attach a gearbox to the motor. The gearbox will convert high rotational speed from the shaft of the motor to lower rotational speed, and often with a higher torque so that larger loads can be moved. Another common type of motor is the stepper motor. Stepper motors operate by moving the motor shaft in steps, hence the name. While the DC motor will move constantly while there is power, a stepper motor will move by one step at a time when a signal is sent via a wire and then stop. How big each step is depends on the construction of the motor. For applications where you need fine control and small movements, a stepper motor is a good choice. For example, stepper motors are used in 3D printers where millimeter accuracy is needed. Stepper motors tend to be much bulkier and expensive than DC motors. They contain multiple coils and more complicated mechanical components, and that reflects in the price. Your circuitry also needs to be more complicated because you need to provide several signal lines of control to make it work. A common problem with stepper motors is that in certain situations, usually under high load, there is a mismatch between the signal that the motor controller is sending and the actual mechanical movement that the motor produces. In simple words, the motor may miss steps and the controller will never know, because usually there is no feedback mechanism to track and confirm movement. A servo motor comes in to fix this problem. A servo motor contains a DC motor, a gearbox, and a position feedback mechanism. This mechanism can make the humble DC motor as accurate as a stepper motor for a lower price, with the added benefit of monitoring and confirming the actual position of the shaft. Servo motors are used extensively in robotics, manufacturing, automation systems, and high-end toys. I'm planning a lecture on stepper motors very soon.